Well, welcome to the Western Hemisphere Virtual Symplectic Seminar again. We're very happy to have today for our speaker, Yuan Gao from the University of Georgia, who will tell us about the symplectic formal neighborhood.
Thank you very much for the invitation. It's a pleasure to give a talk here. Is my voice okay? Okay, thanks. Today I'll tell you about the formal neighborhood of construction in symplectic geometry. In particular, I'll focus on the partial Floer theory for Liouville sectors. So this is the outline for my talk. There are multiple parts. So first of all, I'll give you some background and motivation for this question, and then I'll tell you a little bit about physics in Floer theory on Liouville sectors. Then the third part of the talk is purely algebraic. It's a review of Avamov construction of the categorical form of completion, a notion without using limit and additive topology. And then in the first part, I'll tell you about the idea of proof. Okay, so for our talk, we're going to focus on a Liouville sector, say X, with a defining function on a neighborhood of X. Okay. And to associate to X, there's a unique absolute deformation equivalence, a Liouville pair, which I denote by X bar F, where F can be obtained by quotienting the boundary of X by the characteristic foliation. Okay, so motivating point of view, not quite rigorous, is that we treat F as a divisor sitting at infinity. Okay. So the basic question is to ask, what is the formal neighborhood of F that is analogous to the notion in algebraic geometry? So explain what this problem means from the point of view from mirror symmetry. Okay. So suppose my pair X bar comma F is mirrored to some projective variety Y together with divisor E. Then the homogeneous mirror symmetry for pairs predicts a commutative diagram like this, where this d tilde is some subcategory in the partial Fukaya category of X bar with stop F, whose objects are Lagrangians coming from the cup functor from the Fukaya category of F. Then the full equivalence, yes, I see a question. Oh, sorry, it's not a question. Okay, so the full picture predicts equivalences between all the categories in the sense of mirror equivalences. Oops. So I should probably make it full screen. Okay. So, but there's some missing part, which is the direct category coefficients on D.
Wait, I think I can't see anything anymore.
I can't see anything either.
Okay. Sorry. It doesn't allow me to resume share. Bring your share window to the front. I'm confused.
Right as we see you.
Yeah, but I want to make it full screen.
We don't see it.
It is strange that when I make it full screen, it just disappears.
Maybe it's because you shared the window instead of sharing the whole screen.
Oh. Yeah, I share this application. But so let me see how I can do it.
I mean, or we can just go with this non-optimal version where it's not full screen. I think it's okay. We can. It's pretty big.
So, apologize for that. Let's see. Okay. The missing part in this diagram is the direct category coefficients on D on the device D. But it can be related to the other categories via a restriction functor, namely you consider the restriction functor from the theoretical coefficients on y to that on d, given as the pullback of the embedding from d to y. Then actually that pullback functor factors through the direct category of coherent shifts on the formal neighborhood of y. So we can ask a similar question in symplectic geometry, namely, is there some intermediate category for which the mirror to the pullback factors through? Okay, and in the case of Liouville's model, we know that mirror to pullback is essentially some kind of a restriction fiber functor. And the answer in the case of Lefferts fibration is suggested and outlined in Sato's Lefferts 6 paper for the construction of this formal neighborhood. So the goal of my talk is to somehow extend that construction to general Liouville sectors. But we'll review the setup in Fukaya setup categories. So let's say we have Liouville's model with fiber F, and by the construction of localization by Abzai and Sato, to obtain the formal neighborhood, we can look at the nilpotence of the ambidextrous natural transformation from the Seldon functor to identity. By the nilpotence, I mean, first you look at objects M such that the natural transformation T on that object, which I denote by T of M, can be iterated to 0 for sufficient higher powers. Okay. And you should know that the nilpotents are understood to be in the category of twisted complexes or perfect complexes, which are slightly larger than the actual Fukaya category. So we want to make sense of this for general Liouville paths corresponding to Liouville sectors. So the issue is that there's no globally defined T, but locally you have T interpreted as some kind of continuation co-cycle associated to a positive wrapping of your Lagrangian passing through the stop. However, it is a little bit difficult to define its iterates. To bypass this, we can take the following consideration. Suppose we have this T, then the first observation we have is that if some object is nilpotent on T, meaning that for some power of M, the mth iterative T on K is 0, then it has this obvious consequence that the continuation map from the mth iterates of the inverse cell from K to L to the full complex of K to L is no homotopic. Okay, and this kind of condition can naturally be stated without this natural transformation. But still, the problem is for general pairs, we don't even have this iterates of Serre. So, but there is an equivalent replacement of the homotopic limit of this diagram as you vary M. And it's a very simple object, which is just the Floer homology of K with L. Just take M to infinity. Okay, so we're going to introduce a cochain space, which I know by NC of K with L. More speaking, is generated by intersection points of K with L, but include two copies where you perturb K both small by small positive perturbation and small negative perturbation, and as well as reports on the boundary from L to K, and also those from K to L, but not passing F. So it's some kind of mixed of partial ref theory of K with L, and also the fully ref theory of L with K. I'll give a more rigorous definition in the second part of the talk. So the statement of the first result is following. The first observation is that the nilpotents that I mentioned in a very vague way before have natural candidates, which is just objects in the category D tilde F. They are objects in the image of the cup functor from the Fukaya F to the partial Fukaya. And the first result is that it is possible to construct a chain level infrastructure on those complexes and C, and we call the resulting n infinity category by n. The second statement is that there is a canonical n functor from that category to what's called categorical formal completion of the partial rep category X bar stopped at F along the full subcategory D. And I'll explain this notion in the third part of my talk. So here, we don't assert its equivalence, but it is going to be an equivalence under some further assumptions. And for this statement, we work with arbitrary ground ring K, but for theorems, we're going to assume that K is a field. And everything here is Z multigraded without the condition that C1 is 0. Okay. And some comments about this construction is that, first of all, if we didn't have that stop, then this is related to an early joint work with Ganatra and Bagtash on the Robbins category. And we just drop F, and that's the same as the Robbins category. So in some sense, that's this category N can be understood as a version of Robbins theory for the Liouville sector X. And some basic properties of this category is that there is a natural n functor from that to the Robbins category. It's very similar to the acceleration functor where you remove a stop for the RAP categories. Then I'll tell you about the conditions under which the above functor is equivalence. But may I introduce some terminologies. First of all, say Liouville manifold is non-degenerate in the sense of Ganatra if there is a finite collection of Lagrangians satisfying opposite generation criterion. And the second condition we're going to talk about is one assume that F satisfies stop removal for X, namely you need a shorter exact sequence of categories of this form. And we're going to say that F is a full stop, or rather say its core is a full stop for X if the partial radical category of X is proper. Well, in order for the theorem, for the equivalence to be true, we need a slightly stronger properness condition, which is geometric. So we're going to say that the contact boundary at infinity of X bar has bounded reap dynamics relative to F if for any two Lagrangians and any integer m, the set of reports from lambda 0 to lambda 1 crossing F transversely at most m times is finite. So for m equals 0, that just implies that the partial radical category is proper, but it's quantitative in everyone. And of course, let's say if this X comes from a long Lagrange model with compatible locus, in particular Lefschetz vibration, then the boundary at infinity of X bar admits an open book decomposition, in which case you can check this. But the S1 structure along boundary. Then the main theorem is the following. So here we're going to assume that our K is a field. The simple version is that, well, if we just assume that both the Liouville manifolds X bar and F are degenerate, then the functor above is equivalence. But it turns out that we don't actually need non-degeneracy for the Liouville manifolds. It suffices to assume that the boundary at infinity of X bar has boundary group dynamics relative to F. And also, but unfortunately, you still need some smoothness on the partial graph category. Before I go to the next part, are there any questions? Okay. I probably see one. Oh, sorry.
Are you going to give us some examples later?
Yes.
And while you're at it, maybe I'll ask later. Can you remind me what this D of F is that you are talking about?
D is a subcategory of the partial graph category, which are Lagrangians coming from the image of the cup functor from the Fukaya F. So namely,
okay, that's the image of the cup functor. Okay, I understand. Thank you.
Very say object-wise, it's the image of cup functor. But okay, so the second part is a brief review of the Liouville's Floer theory on the convex completion. And based on which I'll tell you what the definition of the NC is. It's very simple setup. We'll choose to work with a quadratic Hamiltonian. Probably it's not the most advanced approach, but it's convenient for construction. So, so we're going to define the graph of X bar by choosing a positive quadratic Hamiltonian, and the Rutherford coaching spaces is generated by those chords from K to L, and the infinity operations are given by counting of rigid inhomogeneous pseudo-harmonic disks. And something else we can consider is the negative quadratic Hamiltonian negative H. And we can also define a complex, which is generated as a direct product over chords for the negative Hamiltonian negative H, not a direct sum. And there's a continuation map from this the Floer complex for the negative Hamiltonian to the positive Hamiltonian, which can be presented as a rep Floer cohomology cochain co-pairing of degree n. And after which you can dualize this the Floer complex for the negative quadratic Hamiltonian as linear functionals on the rough Floer cochain space for the positive Hamiltonian H. And the Rubin's Floer complex is defined to be the mapping cone of this continuation map in the spirit of the long exact sequence by Schiedebeck, Brouden, Founder, and Wonscher, which relates symplectic cohomology with the Rubin's Floer cohomology. Then there's also a product structure on the above-mentioned Lagrangian Rubin's Floer complex. And for the closed string case was studied in recent works of Schiedebeck and Wonscher and Schiedebeck, Hinston, Wonscher. And for Lagrangian submanifolds, it's a result by Bangladesh and myself. And so there are geometrically defined infinite operations on these complexes. And this direct product definition is necessary for the infinite operations to be well defined. So some way of completing those Floer complexes, for which you can actually define the infinite operations on the completed tensor product of those complexes, and the algebraic tensor product in beds. So you have well-defined infinite operations. And then we want to modify this construction to the partial Floer theory. It's actually a very simple observation. Namely, using a quadratic Hamiltonian, you define the Floer complex by considering in some sense the intersection numbers of time one Hamiltonian chords with some rate of the form F0 cross R plus, where F0 is the Liouville domain whose completion is the stop F. And for appropriate choice of Hamiltonian and almost structure, the intersection numbers are non-negative, and you can consider the subcomplex, or rather the subspace, generated by chords with intersection number 0. Okay. So that's actually the first kind of definition using quadratic Hamiltonians following Sylvan. Then the simple observation is that the continuation map actually factors through some subcomplex, which is denoted by CW star int. We just very small chords. So you choose a Hamiltonian H in a way that's small enough in some compact domain, and you can arrange the continuation map factor through that, because it's presented as a symplectic cohomology co-pairing. It's some kind of disks with only 2 outputs with no input. So you can actually slow down your Hamiltonian on the domain of the disk count. In particular, the image lands in this partial Floer complex. So you can just take your mapping cone but you replace the target by this the partial Floer complex. Then the theorem is that, in fact, the infinite operations on this reverse complex induce infinite operations on these complexes. And it's also a simple observation where you consider all the possible intersection numbers, and you extend them to the chords for negative Hamiltonian as well. You notice that when you count a disk, then you can establish some intersection numbers equality of the inputs and outputs with the rate F0 cross R plus, by noticing that the intersection number of the homologue disk with that F is always non-negative. So yeah, the basic example is considers cotangent bundle of the closed interval from 0 to 1. Then we know the partial Fukaya is equivalent to Morita equivalent to perfect complex over this A2 quiver. Then you can check that this N is Morita equivalent to perfect complex over this algebra.
So I'm very confused.
Yes.
In what sense is the completion of T star the interval becoming T star S1?
It's actually I just start from T star S1 and I remove a neighborhood of the 2 points at infinity.
But I think this is a little bit confusing because, you know, when you remove the neighborhood of the 2 points at infinity, there's still the core circle that lives all the way inside, you know, in T star S1. So how do you get rid of that? I mean, geometrically, what does that mean?
It
I mean, I thought T star of a segment 0, 1 would be instead just R squared with 2 stops, not a cylinder with 2 stops.
Wait. So okay, T star.
So anyway, you're saying we should think of X, X is meant to be a cylinder with 2 stops, one at each end of a cylinder.
Yes, yes.
Okay, I'm happy with that. I don't think it's T star 0, 1, but I'm happy that I understand the example.
And this T and T inverse, they have to do with the two wrapping around the two, the two positive and the negative parts of the cylinder. Is that what?
Yeah. So it's actually just, so you can choose your Hamiltonian so that the confusion map is 0 actually on the chain level. And these are just negative wrappings. So the previous definition, negative, they correspond to generalize for the negative wrappings in each end.
Okay.
And after doing this, allowing negative wrappings, the two objects in the exceptional collection of the rough category actually become isomorphic. So so by construction, there's a natural functor from the partial rough category stopped at f to this n. And this functor is very naive functor. It's just inclusion of the subcomplex into the mapping cone, and no higher order terms. And in fact, many of the functors are of this kind. And that functor sends compact exact Lagrangian to 0, and it also satisfies some deformation equivalent property. You can deform X as Liouville sectors, but it's not quite known that it's deformation equivalent for sub-Liouville manifolds, where you're allowed to change your F to something else, not to an absolute closed set, with while keeping the complement the same. That's not. No. And there's a functor, as I mentioned, is some kind of X-rated functor. And more generally, there are push-forward functors of this form, where you consider removing some components of the manifold F. So it's an analog of the stop removal inclusion functor for Liouville sectors. But it's not known whether there are push-forward functors, but general inclusion of sectors. So in the third part, I'll tell you about the algebraic construction of the formal completion. So first of all, let us review some basic construction of the formal completion from algebraic geometry using additive topology and homotopy limit. So we'll consider some separated notation scheme Y and a closed subscheme. So let's let I of D be the ideal in Y, in OY, defining this divisor closed subscheme D. And so the formal scheme, the formal completion of Y along D is a formal scheme locally given by this co-limit of the spectrum of OX mod I to some power. And U is an open subset of D. So it's the topological points are in D. And for Y smooth proper, there are several functors relating these perfect complexes of these gadgets, the formal completion, device D, and the ambient smooth proper scheme, right? There are two pullbacks, one from the perfect complex on the formal completion to D, and one from the perfect complex of Y to those of the formal completion. And also there's a push forward from the perfect complex of D to the formal completion. And we're going to call that the image of the pullback from Y to the formal completion, the category of algebraizable perfect complexes. That is, the objects of this perf H are the same as those in Y, but you compute the harms by restricting the formal neighborhood, namely you take those limit in the definition in the first. Then the crucial part is to introduce a definition of the formal completion without limit for abstract categories. So that's some early work of Asimov. So here we're going to consider an arbitrary, essentially small infinite category, and T is a full subcategory of C, which you can also take to be a full subcategory of twisted complex or perfect complex. In fact, his work is you can do that for an arbitrary full subcategory of the category of modules over C. Well, for this talk, I'm just going to restrict to actual subcategories. To perform the completion, first of all, let's introduce some notations. So we're going to denote by Z sub T the image of the left unit embedding from T up to the category of left modules over C. So there's a natural inclusion from the subcategory Z sub T to the left modules. Okay, I should mention that Asimov actually completes along right modules, but it is more convenient to work with left modules. So then this being a subcategory of the category of modules has the property that it tautologically defines a bimodule over ZT C op. Left module over ZT and right module C op over C op. And to see this more clearly, one can actually replace it by an isomorphic one. Namely, you consider, first of all, the diagonal bimodule, not of C, but the category of left modules over C. Then you put it back by the pair of functors I had and the left unit functor. Then that's a bimodule over ZT C op. So, and when this subcategory of T is a genuine subcategory of C or perfect complexes, then the above mentioned ZT is equivalent to, the above mentioned bimodule PT is closely equivalent to this pullback. So given a bimodule, we can associate to it a module value functor. So from C, which is the opposite of C, to the category of left modules over ZT, which is identified with the category of right modules over the opposite category of ZT. Then we're going to define the formal completion of C along the subcategory T to be essential image of the above function. And I'll tell you some properties of it. So the first property is that there's always, obviously a function from C to that. And in fact, when T is actually a subcategory of C, then the restriction to T is fully faithful. So when you think about the previous mentioned Fukaya categories, you have this full subcategory D tilde, namely the image of cup functor of the partial root Fukaya category. And we know if we complete that, then this D tilde still sits inside the formal completion as a full subcategory. That is some phenomena similar to the phenomenon in the algebraic geometry completion. And there's also a functor of this one from the formal completion of C along T to the category of right modules over T, which send each object X. So you want to understand X is an object of C, but it's presented as some kind of modules over ZT op. But there is a Yoneda functor, the left Yoneda functor from that, from T to the opposite category. And in fact, this functor just sent X to the right, the pullback right Yoneda module of X. And of course, if
wait, can I ask a question? So this canonical functor, it's fully faithful, right? So I mean, which
one
is the middle bullet point? Do I understand correctly?
It's not.
It's not. Okay.
But you need some conditions. You need smooth and proper for the category C for that to be free. Yeah, but that's the important point. So we're gonna the reason we're gonna assume that the partial root category is smooth proper is because we need something like this to be fully free. And this formal completion is independent of T up to split generation. In particular, if two subcategories split generate each other in perfect complexes in C, then the two formal completions are quasi-equivalent. In particular, the formal completion along T is equivalent to the formal completion along the perfect complex over T. Then Avamov result for the formal completion is that he actually considered an arbitrary separated Noetherian scheme and a closed scheme. Then there's equivalence of derived categories of this form. You complete the derived category quasi-coherent shapes on Y along the subcategory of quasi-coherent shapes on Y with coherent cohomology supported on D. And that's equivalent to the derived category of the algebraic perfect complexes on the formal neighborhood. And in particular, when Y smooth proper, then this gets improved to a derived equivalence on the formal completion of perfect complex on Y along perfect complexes with cohomology supported on D to the category of algebraizable perfect complex on the formal neighborhood. So we're going to apply this construction to the graph category of X bar sub at F. So we get the formal completion, and together with a fully faithful embedding, just mentioned. And to see why this is geometrically important, we see the right-hand side. This formal completion does not involve geometric inputs, namely count of certain homomorphic disks for the category N, not witnessed by the partial graph category, because the complex are generated by both positive and negative chords for the Hamiltonian H. And in fact, the count of homomorphic disks are not just homomorphic disks that you would normally count for defining the Fukaya category. There are disks with multiple inputs and outputs. But the right-hand side does not involve those inputs. Okay. Then I'm going to tell you about the idea of identifying these two notions. Questions? Okay. So to identify these categories, well, the short way, if we assume that both the Liouville manifold X bar and F are non-degenerate, we can use the smooth Liouville structure in gonadal relating this so-called a formal punching neighborhood of the Fukaya category with the Fukaya category. But here we're not going to assume non-degeneracy. So instead, we're going to actually construct the nth thickening of the subcategory detailed. So first observe that the intersection numbers of chords with the array can be extended to chords for the negative quadratic Hamiltonian, where you get some kind of a negative intersection numbers. So you can just define a naive quotient complex by quotienting out those chords with intersection numbers smaller than or equal to m for every negative integer m. Then you play with intersect numbers to deduce that the infinity structures on this category n actually induces infinity operations on these complexes. The category with home spaces being these quotients are not some kind of a quotient categories, but it's some infinity structure on the naive quotients. And there are several functors relating these to the previously mentioned categories, the Fukaya category W and the category N. So there are those, which are all very simple. They're just on the first order level, they're just either inclusions, projections to a quotient, namely a quotient map. And in particular, for every m and m prime with m smaller than or equal to m prime, there is a projection from this complex with intersection numbers greater than m to the complex with intersection numbers greater than m prime. And all these functions do not have higher order terms. And the key proposition is the following. So suppose the contact boundary at infinity of X bar has boundary dynamics relative to F, in sense, namely, for every m, the set of reports passing through F transversely at most m times is finite, then the above categories actually form an inverse system of infinite categories which satisfy degree-wise Dirichlet condition for every pair of objects, and it's on both chain level and cohomology level. On the chain level, it's obvious because every chain map is a projection, so it's surjective. Now, on the cohomology level, you need this boundary dynamics condition to ensure that the cohomologies are finite dimensional and you can work with generators to check the Dirichlet condition. So the corollary of that is actually there is a natural functor from the category n to the homotopy limit of this inverse system and its quasi-equivalence. So we have just expressed the category N as a homotopy limit of some diagram. Then we'll compare this limit with the non-limit definition of the formal completion. So then it's, again, basically the key lemma that Afimov uses to prove his result for the algebraic geometry completion. So the setup is following. So it's slightly different from his version, but this version is most convenient for our purpose. So we'll consider C and T as before. And suppose we have a diagram of an categories labeled by, so indexed by some set I. And we want to have a strictly compatible diagram in infinite functors. It's not some compatible diagram where composition of functors are homotopic. We want them to be strictly agree when you compose. And we need assumptions. First of all, we want every functor to be essentially surjective on objects. And second, we need every right module, every right unita module of Ci is representable by some object of perfect complex over T. And the third, we want to ensure some cohomology level identification, namely you consider homotopy co-limit of the following space, namely you consider the pullback of those unita modules of Ci, which are in the image of Fi, but Fi is essentially surjective, so that's okay. So you pull them back to C, so it becomes a right module, and you compute its hom as modules over C to another right unita module of K, where K is an object of T or a perfect complex of T. And you look at this homotopy co-limit, and you want it to compute the cohomology of the obvious one, namely the cohomology of the hom from X to K. Then under above assumptions, there's a natural quasi-equivalence from the homotopy limit of this diagram to this formal completion. Then for Fukaya categories, we're going to just check these conditions. Okay. So the goal is to show that there's a quasi-equivalence from the homotopy limit of the diagram, which is denoted by n greater than m, to the formal completion of the partial derivative category of X along the perfect complexes over D tilde. So we know that it's equivalent to the formal completion along D. Then we're going to check condition 3 using smooth and properness assumption on the partial derivative category of X. So the key property is that if this is smooth and proper, then the perfect modules over that can be identified with perfect modules. So the formal adjoint of the functor from the derivative category of X to this n greater than m descends to some pullback from perfect modules over n greater than m to perfect complexes over it. And in particular, unita modules are proper because we assume that the category is proper. So the pullback of every unita module from n sub greater than m is actually a perfect complex. Then the other condition can be checked by considering a wrapping exact triangle, as in the second paper by Ganacho Padinchende. we'll just consider some Rabin exact triangle and map them to the category n greater than m. Then we notice that, in fact, the continuation co-cycle becomes 0. So that each object, when you consider it as a module over the category n greater than m, is equivalent to some perfect complex in D. Notice that the Rabin exact triangle in that paper assumes most Legrand stop, but we'll take that as an assumption. We just assume stop removal of that, namely the cone of every continuation morphism of that kind, where LW is some wrapping of L passing through the stop once, and we want that cone. We assume that cone to be in the category of two complexes in D tilde, namely the image of cup. And by pulling back, you get something in perfect complex because you only the formal adjoint only goes to perfect complex. But that's enough for our purpose. Okay. So finally, I want to discuss some further questions on this. So we have mentioned there are posture functors for these categories. You can remove some components of the stop. Or you can even consider some kind of Liouville subdomain in F, and then there's also a posture forward functor like that. But we haven't discussed whether there are posture forward functors for general inclusion of Liouville sectors. That's some question you can ask. And the second kind of question is, can this construction actually be extended to more general settings whenever there is an inclusion type functor? So here we have some kind of cup functor, but for example, you can try to consider some closed manifold and a divisor D. And if you're able to define some kind of functor from the Fukaya F to the target, some version of Fukaya of the ambient manifold, then you can perform this form of completion construction. But does it give you any interesting Floer-theoretic meaning? And the third question actually comes from the statement of theorem, where we'll prove this equivalence without assuming non-degeneracy. And for non-degeneracy, the key property we use to establish equivalence between the form of function neighborhood and the Rabin category is the smooth weak Calabi structure. In fact, we can ask, does that always exist on the Rabin category whenever it is smooth without non-degeneracy? And at least from the statement of the formal conclusion, we can expect that to be true for Rabin categories which admit compactifications. And I've talked to Shell about it. He told me that there's a proof when the Rabin category admits a compactification. I think I'll stop here. Okay, questions.
Okay, let's thank Yuan for his talk. Any questions for our speaker?
Yeah, so I still want examples. So now you can give me an example of some Floer-theoretic category, like a Fukaya-like category, which is isomorphic to like modules over the p-adic integers.
Yeah, integers.
I mean, I thought this was the point. I mean, sorry.
Yeah.
I thought this was supposed to be the point of extending this Rabinovitz category to the Liouville sector. I mean, because now you can do this construction that Paul and I did when we did this homologous recombination which is basically something we did it in T star Sn, but you can just look at now you have sectors, so you can just do it in T star of the disk, and we have this Legendrian stop, whose Floer theory is basically Z mod P. So if you look at a formal neighborhood of this subcategory, this should be what you get.
I see. That's very interesting. Yeah, I haven't worked on that kind of example, but I'll definitely take a look. Yeah.
I mean, I would, I would vote for this being included when you write this up as an outcome.
Yeah. Thanks.
Can I ask a different question about this last question? I'm a little bit confused by what the point is. Smooth, weak Calabi-Yau. I mean, what does smooth, weak Calabi-Yau structure? Sorry.
Yeah.
Okay. So look at the wrapped Fukaya category. It is smooth.
Yes.
Now, I thought the point is that it has this Calabi-Yau structure from this count of Riemann surfaces with 2 inputs and 2 outputs, which are traded non-trivially around them.
Yeah.
Placed non-trivially around the disk. So yes.
Sorry. Shield's thesis actually assumed that there's a finite collection of Lagrangians generating.
To show the map is an isomorphism. Right?
Yeah.
The
To show the map is actually
exists always, but it's not always an isomorphism a priori, at least as that we know at the moment.
Okay.
But in the question, one of the things is whenever it is, I'm a little bit confused because you're assuming that it's smooth.
Okay.
Doesn't smoothness just, isn't smoothness just doesn't smoothness imply that you have a collection of objects that allow you to essentially generate everything?
It says the diagonal bimodule is generally like products of Yoneda modules. But it doesn't say that the diagonal Lagrangian is generated by products. It's a little bit weaker than.
For instance, you could take a disconnected manifold. One component is like actually geometrically smooth, and one component is maybe a not smooth. And then the subcategory, which of Lagrangians in the, on that side will have a smooth category, but the diagonal Lagrangian may not be split generated by products, I think.
But that I don't. Okay, so I think I don't understand what it has to do with the question as Yuan formulated it. That's what I'm. So Yuan, you said the condition that the diagonal bimodule is smooth is weaker than the condition that the geometric diagonal is split generated. Is that what you're saying?
Mm-hmm. Yeah.
Okay. Do we have I know she'll just try to produce one, but I don't think that was an example. Do we have any example of this situation?
I'm thinking about some non-finite type Liouville manifolds.
Okay.
It's
okay. Interesting.
Can I ask a question about this sort of functor used to describe the formal completion again? So
which one? Well, let me.
the bimodule that induces the functor.
Yes, this one.
Yeah. So f tau. So f tau. Okay. So z tau. I can identify z tau with just tau, right? So z tau is quasi equivalent to tau. It's just the image of tau under the Yoneda embedding, right?
Mm-hmm. Yeah.
So you're saying f tau is not always the just the pullback of the Yoneda module. The image of f tau is not just the if I have an object of C, K is f tau of K. It's not just the pullback.
It is
of the Yoneda module. Oh, it is. Okay.
Yeah. Well, yeah. If you identify this tail with this the tail, then it is.
So in other words, can I think of the image of f tau to be just the image of like Yoneda embedding from C to modules over C, followed by restriction from modules over C to modules over tau?
Yeah.
Okay.
So that's actually, yeah, this part is a functor by restriction x to pull back right Yoneda module.
But in that case, that functor is just an equivalence onto its image, right? I mean, sort of like, then it sounds like C tau hat is just equal to like the essential image of pullback from C to modules over tau, right? I just sort of want to make sure I understood which functor. I mean, there's potentially another functor you could try to pull back along a different adjoint or something, but I sort of wanted to, I mean, I think it would be pullback, but I just sort of wanted to ask about that. Anyway, I think you clarified it for me.
I have a quick question. What is the category N of X bar F? Could you explain on that?
What is that? Okay, so I define some Fourier complex to be some mapping cone. Let me try to find it. It's a mapping cone from basically the complex computing right Fourier homology to the partially right Fourier complex. That's the morphism in that. It's this. Okay. And then in fact, you can just look at the infinite structure on the bigger mapping cone, which is the reverse Fourier complex. And this is a sub-complex of that. And in fact, the infinite structures restrict. And that's it.
What is the X bar?
X bar is the convex completion of the sector X. It's a Liouville manifold.
Thank you so much.
Welcome.
Okay, well, if there are no other questions, let's thank Yuan again.